start. We have we recorded? Oh, we are already recording.
No, just now.
Okay. Okay, good. So we continue from yesterday. So let me just remind you, we have an infinitary proposition of formula phi, which we can assume is in the conjunctive normal form. Actually, CNF. So clauses are infinite. We don't say anything about the size of the clauses. They may be very large. We define the poset which we call H of phi. These are finite partial assignments which are consistent in the sense that you can win the game where I play clauses and you extend the assignment to satisfy the clauses, and the only requirement is not play contradictions. So we assume that this poset is not, in particular, the empty set. Start from the empty position and then play the game. So if H of I is it's non-empty, but if it's non-empty, the empty set is in it. So otherwise, we cannot be possibly satisfy the formula. So we assume this. Then we fix an inaccessible cardinal bigger than the size of phi. So kappa is inaccessible. Phi is in the kappa. And then we describe the collection of models we use. I will just draw the picture. I won't write everything. So this is V kappa. We have the set E of alpha such that V alpha is elementary in V kappa. And bigger, I assume that they all contain phi. Okay. And then we define a collection of alpha models. So if you have alpha in E, the collection of alpha models, which we call C alpha, essentially we think that there will be some further theta bigger than kappa, and there will be some elementary submodel here, and then we project it down to alpha. The way we express it is, so these are models M, countable, M satisfies DST minus, alpha is in M, and it's an elementary submodel of these. I think that's all.
You asked that them bar contains V alpha, and that applies.
But this is all, I think it follows.
Well, you don't say it about this then.
No, sorry. You're right. So this is the V alpha. It's not an
No.
So this is not the collapse, it's the transitive closure. And the way you obtain such models is, like I said, you take M, elementary sub big H theta, and then you take the hull of M together with V alpha, and then you take its transitive collapse. That's pi, and then you take pi of M, image of N under this curve. Now, you have to be a bit careful. You don't necessarily get an alpha model. The only reason might be that alpha is not in N. But we will arrange the situation so that we do get alpha. And alpha will be, kappa will be in this model there. And then we project, we would want I mean, I don't have to state it, but in the models that we will care, a pi of kappa will be alpha. These are the models that we will care about, but we don't say it in the definition. Okay, so that's that. Then okay, then we define a collection of okay, then we define the preconditions for each, so for each lambda in E union kappa, we define the preconditions P lambda star. The set of preconditions, it is chains of models where NP is a bunch of models and the lambdas now, what is the lambda of n? It is the level to on which we belong. So lambda m, so m is such that is in C lambda m, or rather, this is a bad, but lambda m is the lambda such that m is in C lambda.
But it may belong to several. You are fixing one of the possible choices of
no, every n belongs to a unique C lambda. The largest element of E, which is in M.
Okay.
So it's plus very long. And then WP was in H of 5, so it's a finite partial assignment. I'd say it's consistent, meaning and the order is Q is stronger if one WP is subset of WQ, so Q. And the other is you can add more models, but you can also fatten existing models. So for every n in NP, there is an n in NQ. Lambda n is equal lambda n. Delta n is equal delta n. Now this is n intersection omega 1. And n is elementary submodel of n. So you extend the finite partial assignment, and you every model may not survive, but some handling of it. Okay, so that is the set of preconditions, and then in order to define the conditions, they are defined inductively. So if you have P in P lambda star, you define the gain. So the gain, which we call, how do we call it, G lambda of, so we define the gain, G lambda of, phi is fixed. And the gain is kind of like what we discussed. I'm repeating quickly, and also so that. So you think of player 1 asking questions and player 2 giving answers. When player 2 plays, so player 2 is actually, we start with a given condition P, which we'll call T0, and we'll define the decreasing sequence of conditions. At a certain stage, one can ask a question. So let's say this is stage n, and the question Qn. So what can Qn be? Qn could be clause in the formula, and then in Pn plus 1, then this is the answer. And 2 plays plus 1 stronger than Pn, such that, can I write something like this? Wpn plus 1 satisfies C. Or rather, picks a literal in the clause C and decides that it's true.
Looking for trouble, but it's fine because I'm not speaking.
I'm looking for trouble.
Because you say there that there is something, but you don't say what it is. Usually in a game, it's better to say what it is, because when you have a strategy,
And so
yeah, maybe like
C such that L belongs to W P plus 1. Is that?
yeah.
So this is question number 1. One type of question, and could be a model M and D, where M is an element of NPN. So it's player 1 can pick one of the models of the current condition and play n the dense set D, which is in M, and it is dense in P lambda n.
So we will have forcibly that lambda n is less than the lambda we are considering.
But what is P lambda? It's the conditions. Sorry, and they are all less than lambda. Yes, by definition. So you don't use the lambda. Less than lambda. And P kappa will be the same definition. So you use all models less than kappa. So you can now, but now this is already defined by induction. So I'm not circular, I mean, vector circularity. And then you have to you have to pick a Q. So then 2 answers by picking some Q. So 2 picks some Q in D. Maybe this Q is not in M, but it can add it to M, and so takes a half of M together with Q. That has the same omega 1 as M. And he picks, or she picks Pn plus 1 stronger than Pn and Q. So
Stronger in which order?
in the P lambda star order. I defined the poset and I defined the order, but we don't use the full poset. The order stays the same when we go to, but we don't use all conditions. We use only those which are good, in which player 2 can win the game. But the game is played in order to define the game. You play conditions in P lambda star. However, all these PNs that player 2 plays, if player 2 has a winning strategy, she has to play PNs which are themselves
in the
winning positions. So she wins for all the PNs will be in.
So you're really using that the game is closed.
Yes. Okay, so So what is P lambda? It's those P's for which player 2 has the winning strategy. That is our definition. Then we, okay, that is our review of what we did. So P lambda is those P's in P lambda star such that 2 has a winning strategy in G lambda of P. We observe that if you take any condition which has no models at all, empty set, MP is empty, and the WP is in H of phi, then player 1 cannot play this kind of moves. So, and you just play by the play inside the H of phi. And so if you start with empty set W, which is in H of phi, it is going to survive. It's going to remain a condition in all the P lambdas. Moreover, the set of conditions for every clause in phi, the set of conditions for which you decide phi, make phi 2, that's going to be dense. Let me write it down. The set of note that this doesn't, I mean, it's true for all others. The set of P given for all C in phi, the set of P in P lambda, such that, which make, okay, I don't want to make Yoko unhappy. So I want to say there is L in C, L is in WP. This is dense.
Under what assumption?
The only assumption is that H of phi is not empty. But anyway, we know if H of phi is empty, then it's hopeless. We can never, the formula is inconsistent. There is no model in any generic extension. So we assume H of phi is non-empty. Then the way things are defined, if you start with any P, if it is in P lambda, that means you can win this game. That means I can always, as player 1, ask the question C, this clause. And you must be able to extend your condition to satisfy that clause, but that's going to be also winning. So these are them.
You are adding by forcing actually a kind of a value evaluation. So this should be dense.
Yes, so it's okay. So now if we force with any of these P lambdas, we add evaluation, we add a satisfying assignment. Or okay, so the question that we want to address is when do we get a stationary focus? That was our goal. Now you could have another goal. I stated Carlson's condition, which some condition, and it turns out that it's the right one for what we do.
So you want a condition which would ensure that this P lambda is...
that I don't know, I want the final one to be stationary. I mean, searching for lambda such that P lambda is stationary self-preserving, But kappa, my hope, I mean, we give ourselves a lot of space. We go to first in assessment. Maybe there is no need to go that far, but we just
So a priori this P lambda may collapse.
for a long time, for many lambdas, they will collapse. But we hope that if we go far enough, we don't. That we get the station acceptance.
We all.
That's
Oh,
what we all want. That's the only thing we want. Okay, so I will erase this. I want to keep this so you don't forget. So what was that condition?
And do you have something similar for semi-proper or proper?
Yes.
So you have a satisfying condition.
But we don't have examples. So, I mean, the examples are for the proper and so on, they're kind of degenerate. I mean, you're doing things, but you don't need to do it. I mean, you already did much before. So, for semi-proper, actually, I don't know.
For example, can you force the forcing axiom for proper forcing with your condition? And using this poset hide the supercompact?
I don't know. Can I force what, TFA, for example?
TFA using this forcing and for the post, I mean.
But this is an instance. I mean, this is just giving you
Yeah,
one,
well, then
and
you
then
say,
you iterate.
Yes, so iterating this poset.
Oh, yes, but you can. The thing is, if you know that there is a proper poset adding a solution to your formula, I call solution a
Okay,
satisfying
then
sign,
you can feed in
then you
inside
can, yes, but it's
okay.
kind of something that
Okay.
you want to, when you don't know that there is a
Mhm.
poset, and you want this to work,
Mhm.
okay, actually, I had in mind to give you another talk, if and only a characterization
Mhm.
of when there is a, say, proper poset of a given size that has a solution.
Mhm.
That's an actual equivalence.
Mhm.
The problem with this equivalence is that we don't know how to use it. It's a translation,
Mhm.
but the only instances in which we know that the good player has a winning strategy is if we already have it.
Okay.
So, okay.
And also here you're giving an equivalence. essentially.
Well, I'm not giving an equivalence. I'm giving a sufficient
Mhm.
that you get.
But if you have a stationary set preserving poset that's your satisfying
Actually,
formula, then you
No, not quite. And here is the problem. You think of your formula, it may consist of two parts. One is the interesting thing, where you can add a solution which by a stationary set preserving forcing, disjunction some other formula which is consistent but cannot.
Mhm. Mhm.
For example, a formula saying that omega 1 is counted.
Mhm.
This method is not going to be able to separate the good part of the formula and the bad.
Mhm.
So, for example, in some clauses I may choose the wrong side,
Mhm.
and then I cannot continue.
Mhm.
The other procedure, which I'm not going to talk today, is actually able to tell you which, how to say, seed that throws away the bad parts of the formula. It doesn't. It's the game that does it for you. So it's.
Mhm.
Don't know how to throw it away, but it's the game. So if you can win the game, that means you can. So. What was the condition? So that's what we call AS consistency. So we have to show that, okay, let me write AS consistency. It is the following, so formula phi is AS consistent if for every S, phi is a, so given phi, we say that phi is AS consistent if for all stationary sets, stationary, sorry, I want to say, well, okay, yes. And if we do in V of the Lady collapse of kappa, kappa is our inaccessible cardinal for every mu, so every mu in V collapse, which satisfies phi. There is an element embedding from V into W such that critical point of J is the omega 1 of V, and it belongs to J of S, and there is an M hat that satisfies J of phi such that J image of mu is contained in mu. Okay, this looks like a complicated condition, but I will try to.
Well, it is much better than the one in Asper and Schindler's paper.
Okay, but you think that, okay, this is kappa. It's really, no, it's about some, the mu's, what are these mu's, sorry? For mu's, what are these mu's? Well, you are going to force with some p lambda, and we saw every p lambda has a satisfying assignment. So mu is going to be a generic for p, the generic also has the models, but take the assignment from the generic for mu lambda. You can stretch it. So I mean, this is not important. Really. I mean, what it's saying that for if you have some mu which exists in some generic extension, then you can stretch it. So mu is here. This is J of mu. Mu is not in V, so I cannot apply J to mu. But I can apply pointers because it's just a function from the propositional variables to 0, 1. So I'm just mapping a variable V to J of V, and I'm just assigning that. So you can kind of, so you move from U to this. This gives you a partial assignment, then you can complete it, a partial assignment of J of phi. And then you can complete it to an actual assignment of this formula. And this J, the critical point is omega 1 of V. You can think of, you have the non-stationary idea, which is precipitous, and then you force with it, and this J will, I mean, it doesn't have to come from that, but that's one way. And you make S, you put S in the generic, therefore omega 1 of V will be J of S. This is how you get those J's. Yeah. So the issue will be, I mean, these J's will actually, in the Aspero-Schindler theorem, let me just finish, they will come from lifting some embeddings from. Okay, yes, you have a question.
Is this definition relative to the particular mu we chose, or is it meant to be for all mu?
We say it's for all mu's, but we really only care for mu's which are given to us by a generic for the p lambdas. But I don't see any case where this is easier to state, and it's a little bit weaker, or not weaker. It's a little bit stronger, but I don't see the difference. So I could say, but
maybe if you put for all mu that are generic, I mean, used by generic over p lambda, you would get an exact characterization of when p lambda is stationary self-preserving.
Oh, you mean where p lambda is stationary self-preserving?
Because it would say exactly for those mu you are satisfying this condition, then you know that p lambda is stationary self-preserving. While if you already started with p lambda stationary self-preserving, then this condition will be most likely automatically satisfied.
Probably right, yeah. Anyway, so it's a condition. So I was going to tell you why this condition is. So what this condition guarantees that so that theorem if phi is as consistent, then p kappa is the stationary self-preserving. And then we have to show how to get to this condition. But I sort of hinted. In getting this condition is actually we don't do anything new. We're just isolating something, and then to verify that condition would more or less repeat what was established. So, but keep in mind this condition. I will keep it on this side of the board, and let's check how the scenario how we prove that p kappa is stationary self-preserving. Well, being stationary self-preserving, positive stationary self-preserving, if there is a projective stationary set of models for which the positive is semi-proper. So I will state that.
What did you say about SSP?
I will write it.
I was just wondering why did you just say that the stationary sets of Granola stationary?
That is the official definition, but an equivalent definition, which is actually not completely trivial, but it's not hard, is the following. I mean, let me write something here. What it means that the poset is semi-proper for a single one. So you have poset P is an element of M, elementary sum of theta, this is countable, and then we say P semi-proper. I mean, I'm just repeating, but for this model N, if for every condition P in M, there is a condition Q stronger, which is M P semi-generic. And then fact, which I won't prove, but anyway, it doesn't matter because we only need one direction, and that direction is trivial. So a poset P is S and P if and only if the set of all N such that P is semi-proper for N is projective. Now I will remind you what that is. I'm burning this pens very fast. So this means for every S subset of omega 1 stationary, the set of, let's call this set S, the set of N in S such that M intersection omega 1 is S is stationary. So projective stationary is more than stationary. It's stationary, but also if I demand that the traces on omega 1 are in a given subset of omega 1, station subset of omega 1, that collection of models is station. So, and in fact, we will only use this, and this is the trivial. So what we want to show is that, and how we going to, in our case, how we going to prove that a model is good? Sorry, that the posted P kappa is semi-proper for some model M elementary. So this is N will be an elementary submodel of some bigger H there, and it will contain P kappa. How do we plan to prove? I think I should keep that slide because that's more important. Everybody knows. So. Okay.
Off it goes. Off it goes.
I will erase. So our plan is to so this is the definition, but this is basically describing how we're going to prove semi-properties. Given M, so suppose theta is bigger than much bigger than kappa, regular, usual, and the elementary submodel of H theta countable contains kappa, phi, etc. Then we say AM. It's not very imaginative. If for every P in P kappa intersection M, basically our idea, the naive idea, how we're going to prove, to witness semi-properness for M. Well, you give me a condition in M, and I have to give you a stronger condition, which is N semi-generic. The naive idea is you have NP, and you have WP, and you just add N. That's what kind of naively you would like to do, and this should witness, provided that you can do it. Now, there are several problems. One problem is that N is not legitimate. It's not a lambda model for any lambda less than kappa, because it's an elementary submodel some H theta, which is bigger. So this is kappa, this is H theta, so you have this N. So you're not going really to put N, but you're going to put N projected to some lambda. So what you want is now I'm back to my definition. I try to motivate the definition. So if for every P there is Q in P kappa, Q less than or equal P, and there is lambda in E such that mu projected to lambda is in N projected is N Q. So basically we put N projected to lambda, so some lambda. In E, we put it on top of the models, and maybe later we add some more models above and so on, but this model appears. But I also, we have to be careful, because I want that pi, pi of kappa is lambda, where pi is the projection from M to M. It would be very easy to find such lambdas. Because all you need is that, if you take M, you take the hull of M V lambda, you would like that this intersection V kappa is equal to V lambda. But by continuity, you have the club many lambdas for which this is true. And so that's This part is easy to arrange, but the question is, why can we, I mean, so I cannot, this is just a definition, right? But this is, says that you are allowed to put this model on top, and you get the condition. I mean, typically you will start with P and just take NP union M lambda, and then WP, and then you will argue that this is semi-general. For some ends, but anyway. So this is the definition when M is good, and then the fact is that if M is good, then P kappa is semi-proper for M. So fact or proposition then P.
Can you remind me what the script E is?
Yes, just a second. For N. E is the set of lambdas less than kappa such that V lambda is elementary in V kappa. So kind of stratifying with V kappa. It's actually not that important. It's just to avoid double indexing. So basically, and we have to show that there are projective stationary many models of which P kappa is semi-proper. Well, we're going to, instead of doing that, we're going to show this. It's a kind of concrete reason why it is.
So basically, M is good if you can put it as a.
Yeah, you can put. Normally, you would like to put N, but you cannot. You just project it to some lambda, and then you put that projection.
For any condition in.
For any condition in N, you can put N on top. And by the way, when you have properness or semi-properness, the construction is always like that. Except there is a difference in the classical. The pose you use some sign conditions which are elementary summoners of H theta, and then you go to some bigger theta star, and you take an elementary summon of theta star, and then you want properness. So the way you, or semi-properness, the way is you take a condition and you cannot put M star, elementary summon of H theta star, because it's too big, but you just truncate it to H theta, just intersect. Here we don't intersect, we project. That's the only difference.
Wouldn't self-generic be, I mean, you said you don't like the good.
Self-generic.
Yeah, or something like that.
Yeah, that's not bad. But it doesn't do the pen. I don't know if I will have enough pen at the end of this talk. Right, so this is the, okay, now I hope you remember this, and now let's just check this. This is straightforward.
Why don't we raise the border because we want to?
No, I think I can rewrite this. I mean, but now this is just a simple verification that you can, but
Is this proposition is good or self-generic?
I wrote good, and I said I don't like the name, but I got a better one, and Grigor suggested, why don't you call it self-generic, and then it's better.
That's very bad because now you will call self-generic in some place, good in others, and we
Just call it good, just call it.
Okay, democracy is not good, right? Was not recorded. We cut it out.
What's good about good is that it is so generic, nobody basically.
Exactly.
But self-generic actually occurs in the literature.
Yeah, and you should not think of it meaning anything profound. It's just the model M is, I mean, we will never use that. I mean, just temporarily. Okay, so let's just, this is a good exercise because everything is there. There's just a straightforward verification, but let's do it so that we
in
get
this proposition, are you going to? You are not going to use the Asper machine consistency in this proposition.
no. I'm just I'm going to use this consistency to show that there are enough projective distinction many good ones, exactly. But for the when do we start? When
We started a bit late, I don't know.
At 8 past.
so can we go until like 15 minutes? Okay. So the ideal proof actually in math is trivial, right? The work is done by the definition, by setting up, this is Grothendieck's approach, right? No sledgehammers, only water.
Generalize so much.
But its generalization has to be done at the right level. But here, the definitions are made so that the proofs are trivial. So, let's say if we, so what is it in, suppose you have this situation, suppose, so I want to prove this, okay? So you give me a condition M and I find Q, such that M, and for some lambda, this is the case, and then I want to show that this condition, oh, okay, I mean, some Q that M occurs is semi-generic for this. But this Q is in P kappa. I mean, it is in P gamma for some gamma, but also in P kappa. And that means I can win a certain game. And in this game, player 1 asks questions, and player 2 plays answers. So the fact that it is good means that if you give me, sorry, what does it mean that this is semi-proper? So that means if I take any condition stronger than Q, but I may just as well say Q because it's stronger means that the more, oh, okay, okay, not quite, because in Q, this model is, but in a stronger condition, maybe this model was replaced by a bigger one. But it's okay, because, I mean, suppose R, I don't know, suppose R is stronger than Q, and then you have that there is some N in MR such that M is, can I write like this, omega 1 extension of N, and it has the same, and actually moreover elementary. And delta N is delta N. And so if you consider, so this R is in P kappa, that means that you can win the game. That means that, okay, so given this and given some D, which is in M, which is dense in P kappa, then I need to find a condition which is compatible. So we need, we need some Q, which is in D.
Well, maybe not Q.
Oh, okay, S. Is such that half of MS in section omega 1 is M in section omega 1, and we need the U less than equal R and S. So given the then set in P kappa, we can find some element of it, which maybe is not in M, but we can add it to M without increasing omega 1, and such that that condition is compatible with our R. Okay? But this is more or less what we did in the definition, except not quite, because you have R, it has its models. Let me call them maybe N0, N1, Nk. And this is the model N here, which is a omega 1 end extension of our model N, right? And then it has some more models. So, you see now, look at this model M. The dense set is a dense set in kappa, but you have this projection map, and kappa gets mapped to lambda. So by pi of, so if you take pi, which is the projection map, pi of kappa is lambda, and pi of V is a dense set in P lambda. And it belongs to M, it belongs here. And this is a sub omega 1 submodel in N. But this is an elementary here, so this is actually also here. And it is still, N also it's dense. And so then we can play it as a move in our game at any position. I mean, you can start with R in the first move if you want. You play N, comma, pi of D. This N is the Nk. Okay, I just take it. That is a possible move for player 1, and then I have to find the reply. But the reply is exactly some S. Sorry, so this was R, and then there was some condition that I could add to the model N. But if I can add it to N, I can add it to this. But then I can also add it to N. This is just a simple thing. Because this model, sorry, this condition S, it is below lambda. It's in P lambda. So it is in the part that is not moved by the projection. So it's an actual condition from the point of view of V. So basically, what is going to be pi of D is going to be D intersection B lambda. And then you have to find some S in that which is compatible with your R.
What is this compatibility is you?
I just want to say that R and S are compatible. So there's a common extension.
That's the next move of the.
Yeah, that's the next move. So you think of the game, and in this, starting from this condition R, it is a condition which means player 2 has a winning strategy. So you can, as player 1, start with playing this. And I have to reply something. I have to pick an S in D, which I can add to N. If I can add it to N, I can add it to M projected to lambda, but that means I can also add it to M without increasing omega 1. That's a simple verification. And then I can extend, the two are compatible. So it's kind of straightforward, and you just going from one positive to another. But the pi, the important thing is that pi of D is just the intersection. Because pi of kappa is lambda. Pi is the identity below lambda. So that's all. Now so is it okay? So this is actually very easy, but again, the whole point is that it should be easy. So now I need to erase everything and rewrite the AS consistency and verify that if we have AS consistency, then there is the set of models which are good. Finally, I mean, CDM, this is the definition, N is a relative sum of H data. I have to show that the set of those models is projective stationary. And that's where the AS consistency. Do I need to write the AS consistency or?
Well, you can start the proof.
I will start the proof, and then at some point we will need to recall what. But maybe I should keep.
You should erase that one.
So right, so.
For every fee there is the embedding, yeah? For every fee in the assignment.
For every new assignment which existed at the
The stationary key.
For every new one, yes. For every fee, there was fee.
The P is the formula and U is the assignment that realizes the formula. So the formula is P. So
The formula is P.
Yes.
Of fees,
So,
the fees
yes,
of
the assignment exists in a generic extension.
I mean, you need to show that the set of good models has a set of good.
If the alcohol is disappearing, you just shake it.
Oh,
Or you should cap always when you're talking or thinking.
we want to show that it's projective stationary, but rather than showing that it's projective stationary, we show that it is a local club. That means I need to define what is a local club. It's a local club. What does that mean? It means that if you give me an X elementary sum of H theta of size omega 1, and let's assume it contains omega 1. Then club many, so X is the model of size omega, elementary sum of H theta of size omega 1, and then I look at some models of X which are good. And I show that club many sum models of X are good. So this is what local club means. A set is collection of countable sum models of H theta is a local club if for every sum model of size, elementary sum model of size omega 1, the models, elementary sum models of X which are in S is a club in X to the N.
So you're proving more than projective
It's
stationary.
equivalent.
Is it equivalent or you need the reflection principle?
No,
to
you
prove
don't.
it?
No, for this, so it's, but this is obviously, again, I don't need the equivalence, I just, so we show that this set is local club. So, K fix that, so we can write X as, so X is of size omega 1. Then we can look at countable elementary sum models of X, which are not good. Okay, so then I want to show that that's not stationary. So we do it by contradiction. Suppose this is stationary. Then there is a reason. I mean, why n is not good? Because there is a p for which we cannot do that. But this is true for stationary many n's, there is a p. So we can do pressing down and we can fix the little p for which they're not good, which is the reason why they're not good. So, and moreover, we can fix some bijection between omega 1 and x, and we can just write x is an increasing continuous union of countable models. X is the union of x psi, I don't know. I don't really want to do that, but increasing continuous, and then we can assume n psi intersection omega 1 is psi for clouding psi. So we just okay. So without loss of generality, I'm a bit sloppy here. We can fix stationary. So without we can fix S subset of X omega stationary, and the fixed P and P in X such that for every n, I mean this is all elementary submodels S consists of elementary submodels of X. For every n, P is the reason n is not good. So there is no Q I will not write everything such that n. There is no Q and there is no lambda. I don't know. Not there is lambda blah blah. Such that this is Q. Just a negation. And the reason is, I mean, right, just negating this, that means there is a P, but again, by pressing down, we can fix that P. Okay. So I call this, I call this to not to be, to make a mistake, I don't know, I call it T. This was S and T is a subset of S for which this P is the same. And this should be T. So S is the set of all Bell models, and then there's a pressing down function on S, and T is the set of P's. Okay, so now we fix some lambda in E such that the hull of in H theta of V lambda intersection V kappa is V lambda. There are club names such. And let's pick, now we will have to remember what was the AS consistency, but I will start reminding you. So it says that something holds in a Levy collapse of kappa. So let's pick a Levy collapse generic. So let H be V generic over the collapse of omega less than kappa. And we have fixed this lambda, and we have now P lambda is a small poset. It has been collapsed, and there are countably many dense sets in it, so we can find the generic for P lambda in this mode V of H. We have the generic. We have the generic for P lambda. Let in V of H fix G, which is V generic for over P lambda. And from this tree, you can read an assignment. Let mu, or I call it mu or mu, which is actually mu g, is the generic assignment. Assignment that we read from is G. G is a generic, but there are two parts, the models and the working part. Just keep the working part that gives you a total assignment. Well, it gives you some assignment that satisfies the formula. And it's mu, but I'll just call it mu because there won't be any other. And so we're going to apply our AS consistency to this mu. Now, this is actually a good moment to remind ourselves what we mean by AS consistency. There is J from V into W. This exists in this model, V of H, such that a critical point of J is omega 1 of V, omega 1 of V is in J of T, and there is a mu hat that satisfies J of phi, and mu hat extends J of mu.
T is stationary in V.
T is, but that's the requirement. T is, this is done in V.
There's not really set of ordinals, right?
Yeah, the trace
But there is a bijection between x and omega 1. I can think, you're right, I can think of T as
That what you mean, or M intersection omega 1s?
but they are the same, because I require
yeah,
them
that's-
tan intersection
okay,
omega
okay.
1 is. So, you're right. So it's,
Where does J map omega 1 V?
to omega 1 W.
to omega 1 W. We don't know. And everything is done in some big collapse. The Levy collapse. Okay, so what is the, I have to tell you what is the good, okay, so what is the idea? Well, the idea is that, let's go back to what we're trying to prove. We have to show, we assume the set of bad ends is stationary, and we cleaned it up, we fixed the P. Oh, sorry, I should have said P, we should make P the generic, such that P is in,
There, fixed G generic for P lambda.
such that P is in G. Okay. So what are we going to do? I mean, we are going to take, we are going to argue that if you take, you have this V and you have W, and you have to show that actually your contradiction would be to find some M in T, which is not bad, which is good actually. But what we're going to do is move to W, and which M? Well, we have X, which is the union countable sequence, so we just apply J to that, and it's the omega 1V element. So the model that we will argue is good in W will be, so if we take, actually I can tell you is the model, actually I will, so what am I going to raise now?
Well, you can write down.
But I'm almost done, so I might as well finish.
Erase that little picture in the middle.
Here?
Yeah.
Okay, so the model N for which we are going to witness goodness is going to be N, which is the hull of in J of H theta of the omega 1 of B union J of P. That's going to be an elementary submodel. It's an elementary submodel of J of H theta. And we're going to show that it's good, but this model is an omega 1 end extension of, okay. I mean, you have the sequence M psi less than omega 1. So apply J to that, and then evaluate it at omega 1 of B. It's going to give you some model, and this N is going to be an omega 1 end extension.
Why?
No, actually, no, it is going to be the,
Isn't that model the pointwise image of this K?
Why don't you take just this model as your witness? The omega 1.
Yeah, I think this is what I want. I don't know why. So I want to take this model. Yeah, this should be my N. But it's important that it contains the. So N is.
So
J,
of N.
huh?
You have written that. So
yeah,
just
so
like
this is
that.
just N.
Yes.
But what is important is that N intersection omega 1 in W. So this N exists in W. Okay. And J of P is in N. And N intersection omega 1 of W is omega 1 of B. This we agree because N psi intersection omega 1 is psi. So it's true when you apply J. This is all I want. And so I need to show that I can take by P, I can take P and I can put N projected to lambda and then WP, and this will be a condition in P.
J of P lambda.
In J of
J?
yeah, so you're right. So it should be J of, not quite right, because we are applying J, right?
Yeah.
So we should take J of NP union N projected to lambda, and then J of WP.
Is it lambda?
But lambda, J of, sorry. The important thing is, let me just basically explain what's going on. We have to be able to win the game from this condition, in this condition. So let's say call this Q. This is the game not in D, it's in W. Think about the kind of moves that player one can play. But you have this M, you have mu, and you have mu hat. So player one can ask a question about some clause, and then you have to extend your W to satisfy that clause. How are you going to do it? Use this mu hat. So so you know that, I know I'm a bit, because I'm out of time, but it is player,
Two can answer
so
at the first.
yeah, so the first type of question, if I ask a question about a certain clause in J of 5, you consult your mu, it exists, sorry, but there I'm doing something which is actually repeated so often that we are describing a winning strategy for player 2, but where does this winning strategy exist? It doesn't exist in W. It exists in V of H. So you say, well, how can we use elementarity? But that's the standard trick. In order to prove that player 2 has a winning strategy, it's enough to show that player 1 doesn't have a winning strategy. So you put yourself in the model W and you fix a strategy for player 1, and you want to show it's not winning, and it's enough to defeat it going outside of W. This is the standard trick. And you defeat it but in this model V of H. So it's there that you know that you have. But since you can defeat any strategy which is in W, somewhere outside, it doesn't matter, that means that no strategy in W for player 1 is a winning strategy. That means in W there is a winning strategy, which cannot, doesn't know about mu hat, but somehow the existence of mu hat tells you that you can defeat any strategy. So let me just say, so this is the kind of type 1 move of player 1, and then type 2 move would be fix a model in the chain. Now let's just consider this condition that we have. Because you have to be able to play the game, so you have to preserve something inductive. But let's just consider this condition Q, and suppose I pick one of the models. But player 1 picks one of the models and then set. But then this model could come from some models of, but then you use the fact that you have this mu, which is generic, and therefore you could extend there. If I play the model,
Well, actually, in that case, you are using G, not mu, because
I'm using.
Because the generic is given not by models and
I'm using
so,
right.
for the first type of clauses you use mu hat, and for the second type of clauses you use G.
Right. So this is, and I don't know, maybe you already said what. Right. So you have to consider case 1 is when I player 1 plays a clause. This we argue that you just follow what mu hat. Case 2 is when player 1 plays a model. Now, this model could be either one of the models of MP, or it could be this model N itself. So according to that, actually you have to split that into subcases. So yeah, in one case, if player 1 picks a model in here, then you use the G. And if player 1 picks this model and then set in Pj of lambda, then you use this mu hat. So you're kind of gluing together. I know this, but this unfortunately. So what should we do? Is it enough to that, or you want me to write down everything?
We can talk later.
Yeah. Anyway, there are the notes, and there is the paper is listed on. Okay, so this is I should finish now. This is not the end of the work. Then you have to show. Oh, okay, but can you satisfy this AS condition? That's a separate thing. But this is not. There is nothing new in that part. So there are many open questions. For example, the thing that I would really like to do is iterate these processes. These are much simpler than, at least on the surface, simpler than their process. And maybe one can analyze and show that you can iterate them without making them fully semi-proper.
So you have a guess for forcing upper bound for star?
Well, we know that it's omega many Woodins, but from classical, I think one should be able to do it from an inaccessible limit of Wood. That means you should be able to easily.
My station separate.
So these posets you forget how they work, what the formulas are. You forget. You just are, yeah, but this is not, I mean, we don't have a general iteration theorem for state-specific recurring. You have to find the class of processes which is iterable and contains this process. Now, we know that certain SSP processes which are not semi-proper can be iterated, like number forcing. And this is a little bit like number, however, it's much more complicated. So, and also, but even if you just want to iterate number on its own, it's quite hard. So, I think it's a whole project. I mean, I think it's a good PhD. Show that this, I may be wrong, maybe this cannot be iterated. That's one. Of course, there are many other questions. Like, can you do a version of this where you try to preserve two cardinals, like proper for semi-proper for omega 1 and omega 1? There are more questions than answers, but this is just a sketch, and to give you an idea of what we do. Okay, so I'll stop now. Thank you. Sorry,